In progress.
Okay. Welcome, everybody. It's a pleasure to welcome you to our program for this afternoon, which will be presented by Kristopher Klein, University of Arizona. Kristopher is a PhD at the University of Iowa and has a degree in mathematics and physics from undergrad. And is going to be talking to us about the sun, which is super cool. I love to use the sun as an analogy for flares from supermassive black holes. It's a terrible analogy, but I do it anyway. And Kristopher is working on it. I think it's a class of satellites. It's just going to be really meaningful and exciting in the coming years. And that is these sort of configurations, the swarm, as they're calling it in the HelioSwarm Observatory, these sort of constellations of the spacecraft. If I'm not mistaken, our very first constellations are going to be solar missions. And so this is really a proof of concept and also some very exciting fun physics for the workshop that we're doing here. So thank you, Kristopher, for giving us your time today, and welcome everyone.
Thank you very much. So thank you for the organizers for the invitation to speak and for all of your attention over the next hour. I also want to thank NASA and NSF for the support they've given that actually supported this research. So the first two parts of this talk are going to be focused on trying to perform some case studies of different thermodynamic effects on turbulent systems, trying to understand different kinetic processes, how those different either instabilities, different heating mechanisms affect the overall state of the plasma system. And then at the very end, I'll talk about that mission that's going to be launched, so-called HelioSwarm, which will launch at the end of this decade, send not one, not a few, but 9 spacecraft into the solar wind. But before we do that, I want to make sure I provide a bit of context about the kind of system that we're actually studying here. Because I know we come from a wide variety of different physics backgrounds. And so I've attempted to encapsulate in a single slide the very complicated study of turbulence and attempted to bring that into a single sentence. Now, with colleagues, we've had 30-minute fights about what's a single sentence description of what turbulence is. The best summing up that I could come up with it is that turbulence fundamentally is multi-scale disorder. You have this very broadband collection of fluctuations. They're irregular. They don't occur at a single spatial or temporal scale, but they're spread out across orders of magnitude in both of those quantities. And all of those interactions are going to, all of those fluctuations are going to non-linearly interact one with another. You get that kind of prototypical forward cascade. Kind of the simplest model that we have is your morning coffee. You put your cream in it to act as a tracer particle, and you stir at the outer scale of the system. That large scale eddy will break up into 2 smaller scale eddies of size L/2. Those will shear one another, getting you a cascade to L/4. And you continue to go down this cascade until some mechanism or mechanisms act to actually remove the energy from the cascade. More quickly than the energy can be sent down to the smaller scale. I forgot I can remove my mask and breathe slightly more easily. So one can work through, and one has, many people have over the more than a century now, worked through the implications of this kind of either forward or inverse cascade in fluid systems. And you can work out different things like power law scalings for how the distribution of the power as a function of scale should arise, giving you the kind of canonical Kolmogorov -5/3 scaling. An example of the kind of scales that we see can be shown in this measurement, measurement of the power spectral density of the magnetic field in the solar wind. The x-axis here is the frequency observed. You have these very large injection scales, which transition into that inertial range, and then the dissipation range where the energy has been removed and leads ultimately to plasma, to in this case, plasma heating. Everything that I said there could be applied to either fluids or broadly to plasmas. But since we're going to be focusing on plasmas specifically here, we want to ask the question of what changes in the case of actually having a plasma system. Well, importantly, one of the most important changes is that you have this magnetic field, you have an electric field. Those will self-consistently respond to the motion of the charged particles. which means that if you have a very simple model for say the fluid motion of your plasma, that is not only going to have the gradient of the thermal of the pressure acting as a force on the fluid element, but you're also going to have the inclusion of both this magnetic pressure as well as a magnetic tension force. Both of those will act to shape the actual flow, and that has to be then coupled in with whatever model you have for the dynamics of the magnetic field. Because of that, you're going to get a variety of different kinds of motions in your plasma that are not present in a simple hydrodynamic fluid, including things like an Alfvén wave. Effectively, it's a normal mode that's driven, has the restoring force that's driven by this magnetic tension term that propagates along the magnetic field. One can work out that if you have this so-called state of critical balance, where the time that it takes this fluctuation to propagate across an eddy scale is the same time as the time it takes the turbulent cascade to transfer the energy from scale L to scale L/2. If those two terms are in balance with one another, you get this preferential cascade, smaller perpendicular rather than parallel scales. So you don't get this nice isotropic transfer of energy to all scales simultaneously. Rather, you get this preferential transfer, those smaller perpendicular rather than parallel scales. These kinds of theories have been worked on for the last 2 or 3 decades. This recent, admittedly biased review of Turbulence by Shikshigan has been on archive now for the last 2 years. Interestingly, though, not all of the power is driven by this local in scale space transfer, but you also do have a cacophony of different kinds of instabilities that will drive energy to finite parallel scales. And we're going to be looking at some of the different mechanisms that can couple non-locally the energy to different regions in this wave vector space. So this represents the perpendicular scales. This represents the parallel scales, going from larger to smaller there. So the other thing, and one of the things that we're going to focus on as one of the 2 case studies here, is trying to understand what mechanisms actually terminate the cascade in this very diffuse and hot plasma that we're going to be looking at. So in the case of a fluid, you have viscosity that acts to actually remove the energy from the cascade, leading to having a transition between the inertial and the kinetic range. When you're in a system that's sufficiently hot and diffuse, the collisions are sufficiently weak that your viscous scale is actually pushed to much further to the right, to very, very small scales. And you're going to have other mechanisms that are going to lead leaching of the energy out of this cascade and the heating of the ions and the electrons. This nice cartoon from a paper that just showed up on archive illustrates this nicely, where you have this inertial range. Then once the fluctuations become of the same scale size as your characteristic ion fluctuations, you'll have some different mechanisms that can act to couple the fields to the particles and lead to the particle heating. And eventually, another square root of the mass ratio further down, so about a factor of 42 smaller, you'll have the same kind of mechanisms that would be accessible to actually heat the electrons. Now, what mechanisms are actually doing the heating here sensitively depends on the actual state of the plasma, and understanding what mechanisms are actually occurring are very important if you want to have some constraint on the relative ion and electron heating in the system of interest. Now, one of the things that I think the heliophysics and generally the plasma physics community has been working towards understanding over the last decade is that the different kinds of instabilities that we'll talk about a few slides down can provide an effective viscosity. So if you have different instabilities that can arise, they may act as a third channel that can extract energy from the field, fields and lead to heating at different scales, and also change the fundamental structure of the turbulence. So those set up some of the fundamental questions that we want to try to understand. What is the actual structure of the turbulence in the inertial and dissipation ranges? What mechanisms are actually leading to the heating of the plasma? Now, this is something that is of universal interest. I won't read you all of these bullet points, but turbulence itself is frequently invoked in trying to understand the dynamics, the transport of a variety of different astrophysical systems. One that I've brought up here is the first one that I encountered, simply because it was written by one of the people on my dissertation committee, Spengler and Armstrong, back in the mid-90s. Used different interstellar scintillation measurements of the density in the interstellar media and found what they referred to as this great power law in the sky in terms of the power spectral density of those density fluctuations, where they found something consistent with that Kolmogorov scaling over, I think that's what, 10 orders of magnitude. So these kinds of turbulent fluctuations are therefore very possibly important for actually mixing the material in the ISM, but also is important for potentially for limiting angular momentum transport, for regulating heat flux, and also for driving stellar and solar wind acceleration. Now, all of these are really interesting plasma processes, but most of them are sufficiently far away that we're never going to actually be able to measure the plasma locally. And so we wanted to find a more local source, and that's where we come a little closer to home in looking at something that we refer to as the solar wind. So back in 1958, Eugene Parker was looking at a nice thermodynamic balance equation between the gravitational impole and the expansion of the sun's atmosphere, and found that, well, the sun is too hot. The surface of the sun is too hot for all of the plasma there to remain contained, and was able to actually produce a model that balanced those thermal and gravitational forces. So the model, which originally was just a hydrodynamic one, later people have added on included in the impacts of, say, the magnetic field, of the rotation of the sun, all those elements. But this is that initial simple model, effectively described what the flow profile should be of this outflow from the sun. Now, several classes here are obviously unphysical, both 1 and 2. Are double valued. 3 didn't agree with the observations that we have in terms of what we expect the speed to be at the sun's surface. 4 right here is what's referred to as the solar breeze, and didn't agree with the pressure boundary conditions at the edge of the solar system that we inferred at that point in time. So he predicted that 5, the solar wind, which accelerated from being subsonic to supersonic through this critical.
What's being plotted on the vertical axis?
So the vertical axis is the speed of it's this UR. I should have used the same. This is from Parker's original paper, and so
Radial velocity.
yes, it's the radial velocity normalized by the sound speed. And so again, yeah, yes, yeah, it's the sonic Mach number. So this solution 5 right here goes through this critical point, right? Critical point where it goes from being subsonic to supersonic at that particular value. Now, there were no observations of this continuous plasma outflow at this point in time, but if you're looking at the date right there, you'll note that in a few years, we had started launching spacecraft into well, beyond the thin onion skin of our atmosphere. And there were, for obvious political reasons, 2 parallel paths that were being taken. And so the first observation of the solar wind was actually made by an instrument that was intended to be a lunar impactor. It missed the moon and instead became an interstellar explorer. So Luna 1 recorded proton currents that were consistent with the densities that Parker was predicting. And then Mariner 2, which was actually on its way to Venus, but happened to have its instruments on at that particular time, was able to not only see that the proton density was correct, but actually found the right speeds for the solution. So this is an outflow that's moving at hundreds of kilometers a second. Question or just? And so those observations were made in the 60s. Since then, NASA, ESA, the Russian Space Agency, et cetera, have launched a whole bevy of different instruments. This is NASA's, they call it the family portrait of all of the different missions that are currently operating that sit between the sun and the Earth's magnetosphere, that kind of magnetic shell that we have around us. You'll see many of these are in, see all of the blue the blue and green ones are the ones that are currently up there. The yellow ones are ones that are currently being built and about to be sent up. Now, this is a nice cartoon, but since we're all looking for something a bit more quantitative here, I've decided to show this plot right here, which shows a selection of many of those same spacecraft. This x-axis right here shows the actual distance as opposed to the cartoon distance between where the spacecraft was operating and the sun's surface. It's logarithmic. You'll see that almost all of the spacecraft are really focused right here at 1 AU. It's because it's a lot easier to get a spacecraft up at 1 AU rather than sending it much closer in or much further out. So many of these spacecraft, WIND, ACE, SOHO, are all operating at the so-called Lagrange 1 point, where you have this gravitational null between the Earth and the sun. And therefore, energetically, if you can get the spacecraft there, you can keep it sitting there for relatively low energy costs for years or even decades. And so what is it we do once we actually send these spacecraft up there? What actual science progress can we make? Well, instead of just gathering in photons or gravity waves from these very distant systems, we can actually measure in situ the electric and magnetic fields, as well as the distributions of the charged particles. And by doing that, we're able to get a good sense of how those two different, those fields and distributions interact with one another, and allow us to get a sense of what mechanisms are actually, what plasma processes are actually arising and under what conditions they are. So for instance, these 9 central plots right here are measurements of the proton velocity distribution made by the Helios spacecraft. And so these are measurements that are made at various distances. So this is relatively close to the Earth. This is about halfway between the Earth and the sun. And this is around the orbit of Mercury, so about 0.3 AU. And then Eckhard Marsh organized this by solar wind speed. These are the various very slow solar wind, and you're moving to faster and faster solar wind, ranging all the way from about 300 kilometers a second, all the way up to almost 800 kilometers a second. And what you see here is that you don't have a nice, simple isotropic distribution for most of these cases, right? This one right here at 1 AU in this very slow solar wind, the distribution of plasmas is almost circular. But if you look at many of the other plots, what you see is this structure that is very stretched out in one direction and very compact in another. This dashed line right here represents the direction of the local magnetic field. And so what we see is that perpendicular and parallel to the magnetic field, you have very different distributions and fundamentally different pressures, which means that you're going to have this departure from that isotropy. That's going to affect the underlying dynamics and then lead to the different things like instabilities that we'll talk about in a few slides. We also see that not everything is confined to a single distribution. For instance, in this case right here, you have this core population and this secondary beam population as well. And so you have these multiple different components that you need to account for if you're going to understand the plasma system. The other thing that I want to point out is that because we've been making these measurements for decades now, and frequently with the same spacecraft for in the case of the WIND spacecraft, now for a quarter century, we have millions of observations. And so if you're looking for a particular kind of plasma, assuming that you don't need to invoke, say, strong gravity, which unfortunately we can't produce in the heliosphere, but if it's a fundamental plasma process, if you're looking for a case where you say have a very high thermal pressure compared to the magnetic pressure, we have hundreds of hours in these very extreme cases. So if you're looking for a local plasma analog, the solar wind is a great place, and we have buckets full of data that we can use. So with that in place, I'm going to actually dive into the two different case studies that we're going to look at. The first of those is looking at different kinds of kinetic instabilities that can be driven by those departures from local thermodynamic equilibrium. And then the second one is going to be looking at the different kinds of heating mechanisms, and specifically looking for one kind of heating mechanism and using our ability to measure both the fields and the distribution simultaneously in order to show that indeed, in this particular case, Landau damping is occurring and is leading to the damping of that turbulent cascade. So this is just, this plot right here is really trying to drive home the point that Eckhard Marsh did not just cherry pick a few cases where he saw a departure from equilibrium. Really, the non-equilibrium structure is seen ubiquitously throughout the solar wind. So these plots are taking those millions of observations from the wind spacecraft and organizing them as a function of either solar wind speed or this quantity we're going to call the Coulomb number. I'll define that in a second here. And then looking at three different rows here, which is the temperature anisotropy. So looking at how wide the distribution is transverse to versus along the local magnetic field. Looking at the temperature difference between the local, between the alpha particles and the proton distribution. That's this plot right here. And this is looking at the relative drift speed between the alphas and the protons. So the alphas are fully ionized helium particles for those not familiar with the parlance. So what we see in this first column right here is that for the very slowest solar wind, the alphas and the protons have effectively the same temperature. But as we go to faster and faster solar wind, their temperatures significantly diverge. We also see similarly an increase in the relative drift speeds between them, and then also a slight decrease in that temperature anisotropy away from unity. However, we can elect to reorganize this data, not as a function of solar wind speed, but using some of our understanding of the processes that would either allow or destroy this departure from equilibrium, namely collisions. So in a plasma, collisions can be, the collision frequency between two different species can be written in this form right here, which effectively says the collision frequency is going to be proportional to the density of the plasma and inversely proportional to the temperature to the 3/2 power. Because the solar wind is diffuse and because it is very hot, with at 1 AU, the total density is 10 per cubic centimeter. The temperature is in the kind of tens of EV. So hot for me is not hot for neutron star mergers, but it's hot enough to drive the collision frequency to a relatively low value. One can use the local measurement of this collision frequency, organize the particular parcel of plasma that you're looking at as being very collisionally dominated or weakly collisionally dominated. The best way that we've come up with doing that by calculating this so-called Coulomb number, where you take that frequency and you multiply it basically by or you divide it by effectively the advection time that it's taken that parcel of plasma to travel from the sun's surface to where you're actually doing that measurement. So R is just the distance divided by the solar wind speed gives you this dimensionless quantity, which means the quantities over here, the measurements over here are very weakly collisionally processed. They've had very few Coulomb interactions. As you move further and further to the right, you see this, the plasma has undergone many Coulomb interactions. And we see for all of these cases here, as the plasma becomes more collisionally processed, it moves to a state where the relative drift between the populations goes to 0, the temperature equilibrates between the two of them, and the temperature anisotropy of a particular species goes to 0. And so this gives us an understanding that the collisions are playing some sort of role in removing this non-equilibrium structure. But for the data where that for that non-LTE actually exists, does that have some sort of dynamical effect on the plasma? And yeah.
So in it's called that community when we have looked for thermalization and equilibration with short range collisions, and there are 3 collisions per particle are enough to get you very close to the thermal. So how is that? These are good collisions, they're long range.
Yes.
How many do you need there, or does that have to be hard collisions, or
No.
are these collisions good enough?
So these are collisions where you have a sum over many collisions that will sum together to give you approximately a 90-degree deflection. That's the kind of
number. Okay.
Yeah. Yep. Yeah.
And you probably need about the same number of collisions.
Exactly. Yeah. And so in theory, everything over here has had less than order unity of those collisions. Yeah. So
isn't that, by the way, what you would usually call Knudsen number, this N?
I think the Knudsen number is slightly different, but I need to pull up my NRL and remind myself of that. Someone wants to jump in and save my lack of recollection.
The velocity of the wind.
Yeah, so
It's the entry path of the particle, which is the velocity of the particle.
So it's a collision time divided by a characteristic fluid time scale. Isn't that a Knudsen number?
yeah, I think the difference, as you said, is whether or not we're using the thermal velocity here versus the bulk flow velocity. And so I think that's the distinction there. So when you have a system that has departed from equilibrium, there's generally speaking 2 different classes of instabilities that can arise. One of them can be understood in terms of the configuration space instabilities, so-called fluid instabilities. If we look back at that momentum equation that I wrote previously, and we replace that scalar pressure with a pressure that has a temperature and anisotropy in it, so both a perpendicular and a parallel pressure, the overall expression for both the magnetic pressure and the magnetic tension are made slightly more complicated. And importantly, this magnetic tension term now has a factor where you have a P perp and a P parallel that both will be impacting how effectively the magnetic field can pull that fluid element back towards its original location. It tells us that the effective alphane velocity of this alphane wave that's trying to propagate along the field is going to be modified by this factor of beta times this pressure difference. That means that if that pressure anisotropy is sufficiently large, you can actually break the restoring force, and instead of having the fluid element being pulled back, it can continue to grow in an unconstrained fashion, which leads to what's known as the CGL fire hose instability. Effectively, if you have your magnetic field line here and you pull it away, the restoring force is not strong enough, and so you get this what's seen as the fire hose instead. So basically, the magnetic field will whip around in that sense. Now, we also have a class of instabilities that fundamentally depend not on those configuration space parameters, but depend on the actual structure of the velocity distribution. These are broadly termed different kinds of kinetic instability. Effectively, if you have a wave that has some frequency omega, you can determine the velocities for which the particles will actually resonate with that particular wave, and the particles will scatter from that particular resonant velocity along paths of constant energy in the wave frame. So if your particles are distributed along these contours in blue right here, particles at the resonant velocity are going to scatter effectively along these black contours here, which represent those paths of constant energy in the wave frame. One can write this out much more quantitatively. It was done back in the late 60s, but effectively the scattering is dependent on the velocity gradient of the distribution function f right there. So if you have this nice isotropic distribution function, you'll have a net transfer of energy from the fields to the distribution. You'll have a form of damping of that particular wave. But if you change the structure of the velocity distribution sufficiently, what you'll get, so here we have a T perp that's much greater than T parallel, and it's sufficiently large that you're actually going to get a scattering of particles so that the particles will actually give up energy and lead to the emission of a wave. And so this is the kind of ion cyclotron wave emission rather than wave absorption. So that's going to sensitively depend on the local structure of the velocity distribution that we have. So that may seem like just an esoteric exercise in looking at the structure of distribution functions. If we take those millions of spectra that we have, those millions of observations, and we plot them in a space where we can calculate a simple parametric model where these instabilities should arise, we see that the instabilities actually limit the overall growth limit the distribution of the observations. So this plot right here is a plot where the x-axis is that relative ratio between the thermal and magnetic pressures of what we refer to as plasma beta. Here is that temperature anisotropy. And if you assume that the only source of free energy available to these instabilities is the proton temperature anisotropy, you can work out a parametrized instability threshold that looks something like this. A, B, and beta naught are going to be slightly different parametric values. These 4 different instabilities that can arise. 3 of them are kinetic instabilities. Then you have this oblique or CGL fire hose instability right there. The colored plots right here are an indication of the probability density of the observed solar wind that we see, and we see that the data indeed does not move dramatically beyond this overall distribution. Now, one could ask, maybe everything is just settled in by the time we've gotten to 1 AU. If you move further, closer and closer to the sun, as was done by the Helios spacecraft here, and make these same kinds of plots, what you see is that the data never really extends beyond these temperature anisotropy thresholds. And in fact, as you move further and further outwards, it seems to basically move along and remain constrained by this threshold as it moves from the upper left to the lower right. For those aficionados in the audience, if the plasma was expanding according to just a simple double adiabatic law, it would we'd expect it to follow along this line right here, which we see very much that it does not. So that it indicates that there's some level of continued heating or some variation from that simple double adiabatic expansion. Difficulty with this is that these models, these parametric thresholds, only account for a single source of free energy, just that temperature anisotropy in that core proton distribution. And as we saw previously, there are proton beams, there are alpha particles, there are the electrons, and all of those may have structure in them or may contribute to the excess parallel pressure that can possibly either add to these instabilities or act to stabilize them. So one can attempt to construct slightly more advanced models accounting for that extra parallel pressure. That's what, for instance, Matt Coons and colleagues did right here, where they effectively said, let's add in all of the different fluid pressures that we can include, both the thermal pressure as well as the ram pressure right here, and come up with these thresholds for both these large scale instabilities associated for the fire hose and the mirror. And we see again, if we organize the observations, that a very small fraction of the data actually moves beyond these thresholds. But none of this accounts for those kinetic interactions, those instabilities that actually sensitively depend on the resonant interaction with the distribution function itself. And so to do that, we're going to need an even more sophisticated model, which is what we'll be touching on here. So I'm not going to go through the expressions at the right. I'll just talk about the overall method that we're doing here. But effectively, instead of treating this as a fluid or a multi-fluid, we're going to be looking at the collisionless hot plasma dispersion function, which effectively says if we linearize the plasma response, we can see a coupling between the current, total current of the total linearized current and the perturbed electric field, and that can be written in terms of susceptibility that's associated with each of the components. And so we can model this as a combination of a proton core, a proton beam, an alpha, and an electron distribution, and all of those contributions together will give us an overall current, and then assuming they're each of them have a bi-Maxwellian distribution, we can come up with a clear numerical solution to the wave equation there. Illustrating it just here, what we have here is the real frequency and the imaginary frequency value. So this is the actual frequency of a solution, and this is either the growth or damping rate, depending on if gamma is positive or negative. These red dots represent the solution to that wave equation that I moved quickly past on the previous slide. And what we see as we move from left to right, as we decrease the temperature anisotropy from unity to smaller and smaller values, is that these solutions, which I've labeled F, they represent the fast magnetosonic mode, which is effectively the acoustic mode that couples together the magnetic and in which the density and the magnetic field fluctuations are correlated as opposed to anti-correlated. What we see is as we go to lower and lower temperature anisotropies, the fast mode goes from being stable, having a gamma less than 0, to being unstable, where gamma is greater than 0. Now, one could, in theory, make this kind of calculation for every single of those millions of different observations that we have of the solar wind, but that you would have to do this for every single point in wave vector space that you care about, and then it would be computationally quite burdensome to do. So instead, I've turned back to actually a method that was first developed in Bell Laboratories, something known as the Nyquist instability criteria, where effectively, instead of looking in an attempt to classify if a particular equilibrium is stable or unstable, Bell wrote down effectively a contour integral using the residue theorem. Effectively, if you have the determinant associated with your wave equation, and you do the contour integral of the inverse of that, number of poles associated with that is the number of stable or is the number of unstable solutions. So instead of going through and actually identifying by eye, if you have solutions that are stable or unstable, you can just perform a numerical contour integral over the upper half plane, and in doing so, say this particular equilibrium is stable or unstable. And that's exactly what we've done. The details of the numerics are found in this paper, and I would love to talk about them at length, but I realize I've already gone on a bit too long at this point. So effectively, we have for each observation, we're going to have a number of different bi-Maxwellian components, effectively the number of them that we can resolve overall, and we're going to evaluate that Nyquist instability criteria as a function of wave vector space, and then be able to determine if a particular equilibrium is stable or unstable, and do it within fractions of a second, allowing us to actually process millions of spectra. We can then use that also to understand the local eigenfunction response of the normal mode that's the most strongly unstable, as well as which of the components are actually driving the instability. So this method actually tells us, here it's the alphas that are actually driving the instability, or here it's going to be the protons that are driving the instability. And we can do that by looking at effectively this quantity right here, where this chi A sub j is the anti-Hermitian component of the susceptibility tensor associated with the particular species that we're looking at. So by looking at this quantity right here, you can see if power is being emitted or absorbed by that particular species. So the first implementation of this was to look back at that beta versus temperature anisotropy plot and look at initially just a few hundred different intervals and classify if those intervals were stable or unstable. And what we found was that a large number of the intervals that using those simple parametric models would be classified as stable were actually unstable. And that's because those simple parametric models do not take into account all of those minor ions or the additional parallel pressure associated with the secondary proton distribution. So instead of just having a few fraction, 5 or 10% of the total observations be unstable, we found a majority, about 54% of these intervals support the kinds of linear instabilities here. Now, one can immediately ask, well, is this actually dynamically important? And so we started looking not at hundreds, but at thousands of different intervals and started comparing the timescales associated with those linear instabilities compared to the dynamic timescales of the system. So what we have here in this black solid line right here is the median value of the ratio of the linear growth rate compared to the turbulent cascade time at that particular scale. So what we see, the x-axis is the radial distance from the sun. So this was using a subset of observations from the Helios spacecraft. What we see here is that while they are not equal to other, the growth rate seems to be about a factor of a third smaller than that turbulent timescale. So they're not equal, but it's also not completely subdominant. So that suggests that these instabilities may be acting quickly enough to at least participate in that turbulent transfer of energy. Now, the final calculation in this kind of growing series was to take about 1.5 million measurements of the solar wind made by the Helios spacecraft and assess how those instabilities vary as a function of different plasma parameters. So whether it's the radial distance right here, the solar wind speed, or that Coulomb number right here, what we see in these three rows is the fraction of the fraction of the cases that are actually found to be unstable, and then the maximum growth rates normalized by in this case the cyclotron time. And this bottom plot right here tells us which of the different ion components are actually driving the instability. So what we see is as we get closer and closer to the sun, the plasma becomes more and more unstable, and the core population becomes more important to actually driving that instability. And as we move further and further away, it's actually the beam and eventually the alpha component that starts to dominate the instabilities that are being locally driven. If we extrapolate this line further and further in, we expect by the time we get to about 10 solar radii, that about 65% of the distributions should be unstable by that particular point. And so that's where we actually move to Parker Solar Probe, and the question of if we actually do see these kinds of instabilities as we move closer and closer in. So Probe was launched back in 2018. Its prime science mission is going to continue out to 2025, and it's undergoing a series of 7 different Venus gravity assists that's slowly lowering its perihelion the closer and closer distances until it's going to be about insular radii, about 7 times 10 to the 9 meters away from the sun's surface. By moving closer and closer to the sun's surface, we're going to get a better understanding of the structure of the magnetic field and the flows in that environment, as well as the accelerations of energetic particles in that particular in that particular environment. So the just as a note, because I believe these slides will be shared, there's been by now several hundreds of papers written using the data from this mission. So I just wanted to point to a few, two of the collections that have been published. The mission itself measures the thermal plasma population, energetic particles, both the electric and the magnetic fields, and it also has one telescope on it, a white light imager that does not stare directly at the sun, but actually stares directly in front of where probe is going to look at the material that the spacecraft is moving through. So it has this white light coronagraph. So what is it that probe is actually seen? Well, it's seen these ubiquitous both ion and electron scale waves. So if you look, so this is time on the x-axis for both of these. These are different wavelet analyses of either the electric fields or the magnetic fields, these top panels, the frequency being the y-axis. And then right here, we see the polarization of the magnetic field. And what we see is that we don't have just broadband turbulence here, but we have these clear, persistent signs of circular or elliptical polarized waves. And so these waves right here are arising at the ion cyclotron frequencies, and they don't just occur for a few seconds, but they're relatively ubiquitous throughout all of the encounters we've seen so far. So probe has so far gone through 12 of the 24 encounters, and we see these waves continuously throughout all of the encounters. So an obvious question is what's actually driving these instabilities? Well, we see that same non-thermal structure that we saw further out at 1AU. So the same kinds of large temperature anisotropies, kinds of core and beam structures that we saw with Helios. We see all of those, but they're even more enhanced. The densities of the secondary populations are larger. Temperature anisotropies are even greater. And so if we go and actually plug the values for these temperature anisotropies in, what we see is indeed instabilities that are predicted to arise occur at the same point in time where we actually see the circular polarization in the fields. So if we take the local measurement of the thermal plasma, calculate the linear characteristics of if we should expect an instability to arise or not, we compare that to the actual observed magnetic fields, we see the instabilities are rising in the same place that we expect them to arise. Now, one of the points that I really want to drive home here is that the nature of the instabilities are fundamentally different for these cases if you treat the plasma as a single proton distribution or if you treat it as a core and beam distribution. The blue dots right here represent the solution that arises when you treat it as a beam and core, and the red case is when you have it just as a single proton distribution that has the same parallel and perpendicular pressure, the same density as the core and beam structure. So they have the same, they effectively have the same fluid moments. They have different velocity structure. Because of that, sometimes you drive weaker instabilities. Sometimes you drive fundamentally different instabilities. For this case of the second interval right here, when you consider the core and beam case, you actually drive these oblique instabilities, while for the single proton distribution case, you get a different class of parallel propagating instabilities. And so that's something that's very important, is that the fidelity of your model leads to fundamentally different results. The other calculation that I wanted to work through, and then I'll take 5 minutes to talk about HelioSwarm at the end, is actually characterizing what heating mechanisms are actually arising in the turbulent plasma. So as a very brief aside, if we go back to our Vlasov equation, effectively asking how does, in the absence of collisions, our distribution evolve when the only force acting on it is our Lorentz force right here. We can write down our expression where the convective derivative, then we have our acceleration right here. It's going to couple into the velocity gradient of the distribution function. You can say, okay, we define a total microscopic kinetic energy of the system, 1/2 mv squared times your probability density at sum over all of the particle, all of the 6-dimensional phase space here, and ask yourself, how does this energy change? Well, this is just going to be J dot E. This is just the work done by the electric fields coupling onto the current. This is just something that you'll find in most of your plasma physics textbook. This is just that work being done. The difficulty is that this term right here requires you to have complete knowledge of the total distribution function at all points in both in configuration and velocity space, as well as the electric field over that entire volume. That's something that you can get if you have a simulation. That's not something that you can get if you're flying just a single spacecraft. And so if we instead define and try to understand the evolution of this quantity that we call the phase space energy density, which is again 1/2 mv squared times your distribution function, but we don't integrate it over over that full space, we can ask, how does this phase space energy density evolve? And we have those same terms. We have this ballistic term right here. We have the coupling between the electric field and the velocity gradient of the distribution. And then we have this magnetic term out here. It's this field particle interaction term that's actually responsible for that work being done by the distributions onto the fields or from the fields onto the distributions. And so if we want to understand the secular work being done by the fields onto the distributions, we can take this quantity right here and average it over some time interval and not need to actually gather up data over an entire volume, gather it just from a single point in space. Effectively what a single spacecraft can actually measure. And that gives us this, what we refer to as this field particle correlation measure. Actually, this allows us to measure locally the J dot E work being done. And so we can do this kind of calculation both in simulations and in actual spacecraft data, and even in very messy turbulent systems, systems where you have sufficiently large fluctuations that you don't have just a single wave nicely propagating along, but a broadband distribution of fluctuations. What you see is if you do this averaging of this work being done, this work being done, you go from effectively seeing this very messy distribution function structure here to this structure here, which gives you this relatively cleaner structure. You have this change from blue to red represents work being done from the fields moving energy to the distribution, or from the distribution moving energy to the fields. And we see that change in the sign of the direction of the energy transfer arises right at this gray line right here, which is the resonant velocity associated with the characteristic waves in this particular turbulent system. So if you go through and you do the linear calculation and ask, where should you see peak damping arise? We see the structure of the work being done actually imprinted into the velocity distribution function itself. And so you can, since for this particular kind of damping, this is a gyrokinetic turbulent simulation. What that means is we've effectively averaged out the very fast cyclotron motion in this case for computational reasons, which means that most of the coupling is only going to arise in the parallel direction. And because of that, we can effectively integrate over V-perp and get these time stack plots right here, where you see this clear bimodal structure. Particles that are slightly slower than the phase speed are accelerated to places where they're slightly faster, giving this blue and then red signature. Now, this is a numerical simulation. It's in a particular limit where Landau damping is the only mechanism that can actually remove energy from the cascade. What happens if we go to the real world? If we actually look at the distributions measured by spacecraft, we can do that exact same calculation. In this case, we're using the magnetospheric multiscale mission, MMS. And in doing so, we see that exact same bimodal structure where you have this blue going to red, that transition arising right at the resonant velocity that we expect to see for this type of Landau damping. And so this is indicative that, at least for this single case study, electron Landau damping is indeed responsible for moving a significant fraction of the total cascade energy. And that gives us an ability to say, for this particular kind of plasma, it is this mechanism that's actually heating the electrons, which we can then hopefully start to apply to our understanding of different astrophysical systems. This, I said that was a case study. This was actually now published last year, but extended that work not to just a single interval, but now to 20 different intervals, where Arya Afshari, who's a postdoc working at University of Iowa right now, looked both at that initial interval and then a number of other intervals, and found that for most of them, we have that bimodal structure arising, and that the total energy being that the total work being done was of the same order as the other estimates for that turbulent cascade rate. And so that tells us that if we can get these good measurements of the local distribution function, if we can compare that to the local electric field, and we can intelligently average those together, we can get a sense of how the fields and the distributions are coupling together, and allow us to get a measurement of the work that's actually being done. So I want to move to this final point just for the last minutes here. Almost all of these measurements that we've made thus far have attempted to get an insight into this very complicated structure, just flying a single spacecraft through them, effectively saying, look, we can fly this single spacecraft up there, and if we assume that the spatial structure evolves sufficiently slowly, we're going to be able to map whatever time series we have, some spatial structure. This is an approximation known as decades. NASA and ESA have started to launch not just single spacecraft, but constellations of 4 spacecraft at a time. Both Cluster and MMS were designed to fly for certain periods in their trajectories, these nice tetrahedral configurations, which enabled them to measure these spatial gradients at a single scale at a time. So Cluster was focused on trying to understand what does the ion scale structure look like. MMS was designed to go to even smaller tetrahedral configurations and ask questions about what's happening to the electrons. How are they coupling to the electron scales? What we are working towards with the HelioSwarm mission is not to just be focused on one of those scales at a time, to actually have an entire observatory of 9 spacecraft which are situated in such a way that we're going to have simultaneous coverage of scales ranging all the way up to 3,000 kilometers and going all the way down to 30 kilometers. So we'll be able to actually characterize that cross-scale transfer of energy and simultaneously look both in the MHD, the transition, and down into the ion region. So this is a mission that hopefully that will play, was just selected by NASA to launch in probably 2028 or 2029. And it is not going to sit at the Lagrange 1 point like many of those spacecraft that I previously talked about, but it's going to be in this so-called lunar resonant orbit. This plot right here is an equatorial projection of where the observatory is going to be. Earth is at the center. Numbers for this plot are in Earth radii. Where the observatory is this black dot. Moon is that dot right there. And so it uses this lunar resonant orbit to move around and sample both the pristine solar wind out here, as well as the magnetosphere, this blue area right here, and then this so-called foreshock region where the solar wind is magnetically connected to the magnetosphere, so it's magnetically connected, but it's not actually within the magnetosphere. And we therefore expect waves and other structures to be driven by the interaction between the solar wind and the magnetosphere. Now, these plots right here indicate the relative locations of this of the 9 spacecraft in the overall observatory. As you see, many of them are going to be tens of kilometers apart. Others of them are going to be thousands of kilometers separated. And that's going to enable us to do a wide variety of different kinds of analysis, whether we're calculating things like cascade rates, whether we're reconstructing the magnetic fields, or if we're looking at to calculate different kinds of statistical measures, the local turbulence quantity. So I've moved past the hour, and so I thank you very much for your attention and look forward to any questions you have. So thank you all.
What useful lessons can we derive from these solar wind studies to apply to other astrophysical objects, perhaps more extreme, like the ones we're discussing here?
So I think coming up with different prescriptions for QI and QE for understanding if it is Landau damping, you should expect this much energy to go into the ions and the electrons, and then using that as a potentially a subgrid model is one of the obvious implications that Elliot brought up on Tuesday. I think another one of the insights is that, as was suggested in this plot right here, understanding if we do have all of these different kinetic instabilities actually arising, especially in these high beta environments, how does that actually create an effective viscosity that's going to lead to a difference in how the energy is transferred across scales? And especially since many of the systems we're looking at are thermally dominated, or at least parts of them that are in this high beta regime, I think getting an understanding of what role these instabilities play, role these instabilities play in this environment where we can actually identify this plasma is unstable to this, and this is the strength of the wave that actually grows out of it. I think including that potentially in a subgrid model, or potentially just having an understanding of it would be useful.
At one point, you showed that there was this drift between the alphas and photons that was being reduced as we went out in the solar wind. I was just curious, what is the intrinsic?
That's a great question, and it's one that there are a number of different theories about. There are some people who claim there's sufficient magnetic mirroring that would lead to the acceleration of a secondary population. There could be different mechanisms that then lead to basically, if you have a single population and it's been mirrored forward, you get this large, call it a strawl along the field, and then collisions could potentially eat away at some of the lower energy particles, leading to the formation of two populations. That was a theory that was proposed back in the 70s by, I think, Marsh and Levy. But there's also the possibility that instead of relying on just that kind of mirroring, there's the local generation of parallel electric fields in the near sun environment. So basically you have these much larger amplitude structures, whether they be switchbacks or other kinds of structures that have a larger amount of compressive fluctuations. Most of what I've talked about here are these transverse fluctuations. There's also the possibility of having these compressive fluctuations, which will have a larger E parallel, though some initial simulations by Anna Tenerani and some of her research group actually looked at the E parallel that can be generated by these switchback structures as they decay away, then lead to the acceleration of either some portion of the proton distribution or of the alpha particles themselves. Not plotted here is you can actually have a very similar distribution of the relative drift between the secondary and primary proton populations. The actual break in Coulomb number arises at a slightly different point, but it has the same qualitative behavior. And so what mechanism is actually arising is something that we're attempting to use data from Parker right now to classify. And I think a lot of that, based on other slides I didn't have time to go through here, is larger amplitude structures that are arising near or within the so-called alpha surface. This plot at the sun, to my knowledge, has not been constructed. I've seen a few things that are in draft right now. The difficulty is at the sun. We don't, R is relatively small. The other thing that, even though we have had 12 encounters thus far, almost all of them have been very low velocity. So I note, well, you see right here, we have this wide range of velocities from 300 all the way to 600 kilometers per second. Parker has, for the first 8 encounters, seen mostly 300 or 400 kilometer per second solar wind. More recent ones, it's seen slightly faster. So we simply don't have the statistics to fill all of it out quite yet. So that's something that needs to be done, has been done with Helios data, which covers from 1 to 0.3. We see a pretty similar trend there. It's not clear. One of the things that can be done is effectively varying what this R is, and instead of putting it at the solar surface, attempting to create a best fit or an imaginary surface where you say this is the surface where the collisions start. And if you build a model for that, you can see that the best fit to the collisional relaxation associated with that is not at the sun's surface, but rather at the alphane surface, where you have a transition from a subalphenic to a superalphenic flow. So basically, instead of using the thermal velocity, using the alphane velocity to characterize that Mach speed. And so that's work that Justin Casper and I think, published 2 years ago now.
From somebody completely outside the field, these talks are meant for people like me. Just a general question. Did I understand you right that you were looking at data in a turbulent regime, and then in parts of your talk, you were trying to understand it through what I would call linear response?
Yeah.
And then almost there were 60% instability.
Yes. Yeah.
Which appear not to be surprising since the data is in the turbulent regime, which is effectively nonlinear physics, and you're doing that. But perhaps there was something to learn from there when you were analyzing linear response at each wave vector or different wave vectors. Is there something to be learned about the scaling at wavelength scales or at frequency scales in turbulence from the distribution of the linear instabilities that you found?
Yeah, and I think that is important work that has not been done yet, but that can be extracted out of here. I think this represents the kind of the first calculation there, in which we said for the maximum growth rate, comparing what the linear growth rate is compared to the time scale associated with the nonlinear transfer at that single scale, but repeating that work and looking over the entire spectrum over the entire spectrum and see, I think there's more insight that can be drawn out of that. Yeah.
Which is yet to be.
Which is yet to be done. Yeah.
So one of the, I think, open questions when you talk about solar turbulence is how is turbulence driven in the first place? So when you have large scale fluctuations, these can indicate many ways.
Mm-hmm.
You can have an interaction between two waves, you can have an interaction with a wave and the gradient, so on and so forth. So is HelioSwarm going to be able to tell us something about that specifically? Basically, at the injection scale, so even maybe even larger than the inertial range.
I think that for the case of the pristine solar wind, that insight is going to have to come from Parker as it moves closer and closer to the sun and looks to see whether the different models for reflection-driven turbulence, where effectively sun is proposed to drive mostly alphenic fluctuations away due to the gradient in the magnetic field, some of that power is reflected backwards, and that leads to that coupling and initiates that turbulent cascade. For closer to home, for within the magnetosphere, we are going to have strong driving and injection at scales that are slightly larger than HelioSwarm, but I think may still be capable of giving us some insight. But HelioSwarm fundamentally will be focused on that kind of middle of the MHD all the way down to and then through the ion regime. So that's kind of the region of the box that we're looking at. There are a number of missions that are being proposed for decades plus from now that are going to not be limited to 1,000, but go out to 10,000 or even larger scales, try to understand the connection between the injection and the inertial range.
Well, relatedly, maybe, which is the minimum number of these spacecraft that you need to ensure that you can cover like a good range? Because now you have 8 + 1. Okay, let's say the one breaks.
Yes.
What is the minimum number of operations?
7. 7 is the number. So effectively, in order to cover them and to get the tetrahedral and baseline coverage that we need for the kinds of analyses that we're going to do, we need 7 in order to get those separations. Once you go down to 6, you can't form a necessary number of simultaneous tetrahedra, and you lose that baseline coverage. So 7 is kind of the minimum. 9 gives us more hours and even wider ranges of scales that we can cover. Thank you all.